Thank you for coming to CCA. Welcome, welcome. I'm very happy that you guys joined this program. Being one of these organizers who didn't do any work. I mean, the main work was done by Jiske, John, and Paco, and and Peter. Like, a lot of people in the background, and they do all the work. I'm mostly just providing moral support. I'm also giving this talk. Deep learning as a last resort in galaxy formation. I'm trying to switch it into a galaxy formation direction. I gave a very similar talk before at this venue where a bunch of rich people were trying to figure out what to do with aliens, pretty much. Seriously. But I switched it for galaxy formation. So they were trying to figure out, where's the next thing to put money in. So that's the
Do you mind standing near the podium mic for the people on Zoom?
Sorry, say again.
Standing near the podium mic for the people
Okay,
on Zoom.
I will stand very steadily here. All right, I will do that. And I'm showing this work about, how do you use deep learning as a last resort in galaxy formation. Don't just throw it there. So there are two reasons why you want to do deep learning sometimes. One is you really can't have any other methods you understand. Then you go use it, right? Because a lot of people will come back to you and say, hey, it's a black box. What's the problem with you? Why are you trying to use deep learning, which you don't understand, which is black box, to understand, I don't know, dark matter, dark energy? That was my complaint when I started doing it, 2012. Lots of complaints. And in the other situations where, it happens very often, there are some researchers or my own students or postdocs who want to get a job outside outside astronomy and want to be in the industry, and it's very popular to get recruited if you know some machine learning. So there are really two big reasons to do it, I think. And I'm going to talk about the first one. I luckily don't have to deal with the second one right now for myself, but here's why I'm showing work today about what we're doing that could be interesting. I'm showing some of the pictures because there are a lot of names. I don't think you recognize all of the names, but some of the people who are doing a lot of heavy lifting, some of them, Miles and Christian. Christian, can you raise your hands? I don't know where Miles is. They're giving the tutorial later in this week. Actually, Miles in this afternoon, correct? And Christian on Friday. Thank you. And so they will tell you more about the stuff I actually will touch on today. So we've heard all the hype, and you guys probably seen all this. I was going to explain what neural network is, so I decided to type in a line that says a neural network is a digital brain that lives inside a computer. This is actually OpenAI's founder has said this, not me. So that's the image generated by DALL-E when humans typed in this sentence I just said. What is this based on? This is based on something called transformer, which is CLIP, and something called Glide, which is a diffusion model. I'm not going to go into the details of these super advanced machine learning algorithm, which we have used actually to do turbulence simulation accelerations. And actually, Ronan, who's a physics grad student from Miller, has used it to do cosmological simulations with the score-based model. I won't go into those details yet because we haven't done too much of these in galaxy evolution or, these kind of analysis. Mark might have some work in this direction yet. Maybe it's coming up. I know there's a few work right now that's in progress. I think people see nodding the head. Feel free to raise your hands and ask questions at any point. I'm happy to be stopped anytime. Another input, teddy bear painting a portrait. Similar, this is from Meta. They actually generated a video from that sentence. So I mentioned earlier the CLIP model, which is a language model that's based on transformer. That one we actually used, they trained on a huge corpus of caption video and text. And that's how they figure out how to generate this. The generation part is it going from noise to this video is the diffusion model. For those who are interested, should Google it and try to figure out what's going on here. There's a lot of materials online. Good thing about machine learning is that you can pretty much try to learn it online by yourself. It's a little bit intense because there are a lot of materials. But I think there's a lot of good materials too. And neural network can write its own code, or the clickbait version, artificial intelligence reproducing itself. This is Copilot running in Visual Studio Code. And if you type average runtime, this is what you typed in, and it actually pops out the code for you. You can also condition on your own GitHub if you want. So it'll be even more specific to your own writing of the code. Some people claim that very soon we won't have a lot of GitHub code will be written by Copilot. So the training might get very confusing because they're training on the code they wrote yourself. So same thing for the ChatGPT. When I have to confess, I did use ChatGPT to actually grammar check and make my letter recommendations much, much more concise and precise. And people have been using it to do many things. These are the joke that they wrote because so many people are using it. They actually are at capacity. I heard ChatGPT servers are slow because they're trying to teach AI how to be patient. The ChatGPT servers must be stuck in traffic in the internet highway. these are generated by ChatGPT itself. It's not written by us. It's a joke, right? And it actually reflects intelligence in some ways for some to argue. It learned from a huge corpus online of all the text, and it created all these jokes that I think is pretty cool. So we won't go into discussion about whether there's true intelligence there, but they're doing pretty good emulator intelligence, or at least humor. And that's how I'm feeling right now. A couch potato, that's what you generate if you type frame photo of a couch made of potatoes by Imagen. Same technology, yes. Oh, you feel like couch potato too? Is that why Eric's pointing at it? Oh, I love potatoes as well. Or this is the snafu version where a young couple walking in heavy rain. I mean, both this and this was generated by the same thing I talked about, transformer plus diffusion model. What's wrong with this one? I pick one that's funny because it's wrong. Come on, guys, you know. It's the entertaining part of the talk. Later part is not so entertaining. What's wrong with this one? I will go again. They were conjoined twins. They're not a couple walking in the rain. I mean, yes, they can love each other a lot, but still. So there are just, a couple of recent examples that happen within the deep learning community. There's new ones that I didn't put on. For example, they can write text. It generates a whole video, like a 3D video in time series. And it's just a piece of text. It completely blows my mind. But do we absolutely need this art generated by neural network? Do we absolutely need the network to help us write the code? I have to say yes, but at least for my grammar check, it's much better than Grammarly using ChatGPT. I'm worried they will start charging me. I argue today that there are situations where deep learning can be used as a last resort, and that is interesting. I have very personal holy grails here as a cosmologist by training. I like to connect dark matter to galaxies, and I like to accelerate expensive simulations. So there are reasons why I like these. It's a very personal choice. I see many good examples that you guys have shown that are very different, like dealing with the data. I was very shocked by the talk where they did find mergers with sky background, right? So I actually texted Robert Lupton, right? Like, what's wrong with the Sloan sky background subtraction? And he's actually looking into it. Don't laugh. He was very serious. And so I'm going to not be able to cover all this ground because we've done a lot of work in these directions. And I'm not going to be able to cover everyone's work. So I'm just, as advice, I try to, sort of advertise my students and postdocs work a little bit. So accelerating expensive simulations. This is, I'm not going to play the movie yet. This is a very complex plot. I'm only going to show one plot for accelerating simulations. This is a turbulence simulation generated by Athena++. This is work led by Kimberly Stackenfeld, who's a research scientist at DeepMind. And also work was along with Jim Stone and people like Miles and a lot of people from DeepMind, actually. What we're asking them to do or trying to do working with them is to predict the next step turbulence simulations from Athena++, given, X time steps before. And it wasn't using transformers back then because that was before transformer was a thing, surprisingly. We were working on 2021 and transformer wasn't that useful back then. We did have work later on to use transformer to accelerate simulation in turbulence simulations, which I don't have movies to show, so I'm not showing you, but I can point you to references later. So without further ado, we're showing the frequency on the lowest. Okay, let me just show here. Can you see yes. The frequency on this is just basically a k-bins, the amplitude in this direction. And for density, x velocity, y velocity, c velocity, and pressure. Here is the ground truth on top and the predicted rollout, which means if I make the next prediction, next time step, I'll take that output, and run it through our model and predict the next time step. So any errors in prediction would exponentially, grow. So that's what rollout means. Don't let people say, oh, you should use the correct one and predict every single time step, because that's wrong. So I'm going to show you what we have. And just to mention, a lot of people say many things about what they can do with turbulence, accelerations, simulations. A lot of them, we've done all the benchmark, and our work is actually at least as good, if not better than all of them, right, at 2022. And we were able to roll out many, many more time steps than most of the work. And you can see that the ground truth looks okay compared to the rollout. The two colors, you can show the differences as you go forward in time. And at the end, it doesn't look as good, but it's a turbulence simulations. Things are very complex. the dark matter simulations we can do much, much better because it's a much easier n-body code. So this is what we had 2022 and was accepted in International Conference on Learning Representations. And we had other publications coming up. The ideas we have here is not just to accelerate the simulations, but also learn the equations in the simulations and find the closure relations for those who haven't heard much about this. There are closure terms that you can close certain equations when you run the simulations that can be learned from the simulations. So that's what we're trying to do next. So that's sort of a preview of what we're doing in simulation accelerations. Another holy grail, connecting dark matter to galaxies. What do cosmologists want? Surprisingly, we want these galaxies to be correctly in place in our simulations. And why is that? It's because we can generate the dark matter simulations in various ways very quickly now. Maybe not as high resolution as you want, but we can do quite well. And of course, we can run large volume, high resolution simulations thanks to Illustra's team, beautiful movies, right? Say, can we get 1 million of these following, which takes about 30 million CPU hours each. So it'd be way too expensive to run these many simulations. Why do I need 1 million? Because we want a forward model universe with all these variety of parameters in cosmology and astrophysical parameters and find out what is the truth, the underlying latent parameters of the universe, comparing to what we observe, which is galaxies. So that's hard. So people have been doing this for decades, right? I'm not the first one. We have people trying to paint galaxies onto dark matter halos. We have heard of HOD, we have heard of SHAM. There are way more experts here that can tell you way more about this. I don't know all this stuff, but what I can tell is that people have been painting galaxies in certain ways. The simple one like HOD, there are many versions. They're similar analytical ones that does not necessarily take into account all things, but we can marginalize over parameters of the formula. This is why cosmologists love to use it. There's a risky one. I will call it risky. Say if you have at least one hydro simulation or simulation that you can trust that models universe correctly in a small volume, can we try to use many methods to learn from that one and just generate way more, right? Using machine learning. So we've done a bit of that. This is way in 2019. In machine learning years, 1 year is about 10 years in cosmology, in my feeling. Like 2019, I forgot what the paper is about already. I have to look back. This was a student from Hong Kong, actually. Now I think it's a grad student in University of Wisconsin-Madison. And what he did is that he came and worked with us and say, okay, if I input dark matter simulations on one end, can I paint the galaxy just to get the number densities right? This is before a lot of people were doing this, right? And we were like, okay, I don't know what to do. So HOD is that side. Okay, let me point. HOD is here, and you can see that it will just give you a massive galaxy in the center, and maybe there's some Poisson distribution of satellite galaxies around. But what you want is these, right? This zoom in version. What's much more complex in Illustris. So then what we did is that we used something called cascade model, which is basically a variation of convolution neural net. Why do we call it cascade? What we did is that we look at a map of these dark matter simulations and hydrodynamic simulations, and then we find all the pixels that actually has galaxies. Then you do convolution neural nets to find how many galaxies are there by regression. So you don't, because there's a lot of empty space otherwise you basically fail quite quickly because it's so empty. You can see this space. It's impossible to train because there's too much emptiness basically. So that was good. And this is showing some of the statistics cosmologists care about because we want to use this for actual analysis cosmology surveys. Power spectrum, the frequency, the scale, and you can see that the cascade model is this very cool purple-ish pink color, and see that HOD is this one, and the target is the blue, and you see that they fit quite well. They're not perfect until the smaller scales, but they're much better than HOD, and it's much better in bispectrum. It basically fits perfectly for the using cascade model. So we're very happy about that as a cosmologist. There are other summer statistics we looked at and we were quite happy. And then the next thing we did is Noah Kasmanov also actually looked into this, also with us. And you can see that it's very hard to do with dark matter. This is this map. And then you're trying to paint the galaxies, right, for the target. And it's super sparse. HOD will give you that, and our model, which is basically a convolutional neural net, will give you this. And showing that this is also working with a slightly different convolutional neural net model, and we were pretty happy with not just predicting number of galaxies here. What we did here is predicting also the stellar masses. I should have mentioned this is the stellar mass that we predict. The last one is the galaxy number density. This one is stellar masses. We do it step by step. Then we got Jay Wadaka, who was a grad student now at IS postdoc, coming to us and say, hey, can we just do this for maybe painting the H1 because there's a lot of H1 surveys coming up. So can we go from, well, this is just showing illustrious TNG, which is the truth, what HOD would paint, and what the UNet were able to do. And I know it's not obvious why it's looking a lot better, but you can see that the UNet actually looks very, very much like the illustrious TNG, and this one shows the differences between the UNet and the illustrious TNG and HOD and illustrious TNG. You can see that there's basically not much highlighted clumps, which means they're quite different in that areas. So this was also using similar technology that we showed before, convolutional neural net based, but generating H1 gas. So we're pretty happy from dark matter. This is the model that we actually use. It's very similar to all the stuff you've seen before. One thing I like to show people is that you can actually understand neural network by sort of intuition building. If you have a dark matter input right here and you want to generate the H1, you actually want to go further than where you want to generate the H1 patch because you have influence from the outside. And you also need to decide at which point, these are a multi-scale, contracting of information that you want to distill to the network, right? So you want to decide at what layer of neural network that has what resolution of information to be passed along. So there are determinations when you run this code that how you would design the network. It's not vanilla and just plug in and run. And here, then we do a little bit more, right? Because we did all this stuff and say, okay, we can use convolutional neural net, you can learn a bunch of stuff, but can we get at the equation? So not just representing the learned expression as a network, but also getting equation out of it. So this will come back to symbolic regression. You'll hear from Miles Kramer later in this afternoon in the tutorial about how to do this. But this was one of the problem we applied this to. Anna Maria Delgado has worked with a bunch of us, and she's now a Harvard grad student. And what we're doing is that we look at, if this is the halo model, people have seen a lot. This is halo mass on the x-axis, number of galaxy on the y-axis. And we want to figure out how to predict these properly with learned from the simulations and using symbolic regression to find the correct equation instead of using HOD. So that's any question about what we're trying to do. I'm just going to pause for a little bit because we went through like 3-4 papers already. This is like an overview of what's happened. Yeah. All right. So we have illustrious simulations. It has this dark matter component. We want to learn how to paint the galaxies, and we want to not just how to paint it, but also find the equations that painted it from the neural network. Okay. So the two-step process. The first thing they did is actually go back and say, okay, find all the relevant parameters that might affect the number of galaxies in each of the halo. They look at the mass, environment, and concentration, shear, the spin, Vmax, all the stuff that you guys know better than I do. Number of subhalos, Vmax radius, velocity dispersion for different halo masses, right? And then they try to come up with an equation. This is actually an equation we did find. We want to be able to use the HOD as a base. We start off with the HOD base, but then we add, we let the machine learn to find out the machine learning algorithm and symbolic regression to figure out what these parameters are. So we feed in a bunch of these, right, and let the machine decide which one is important. And these are the final equation. And you're like, what the heck happens? So I'm going to show you a little bit how to do symbolic regression, but Miles will do an actual tutorial later and give you an additional taste of how to do this. But Miles will actually teach you how to do this. I'm going to show you what we have done to go from illustrious simulations. It finds a bunch of variables that might be important, and then we basically found the equation. So like, how do we jump from these steps to this step? But to do this, we actually will have a foray into planets, our solar system. Yes, please. I have questions.
So in the earlier papers that you showed, you painted on gas and galaxies from maps.
They're map based.
Yes, but in this case, you're using halo parameters.
Yes, correct.
So you're using the halos found by Subfind or whatever halo finder is used. Okay.
Very true, very true. This one we actually not using the maps for reasons because I think they decided it's easier to start with all the halo parameters we have. And there's quite a number of them. And there are many equations you can form. So how do we go from a list of parameters from those maps to a list of parameters and to equations? Yeah, okay. But we're going to do a foray into solar system. So this is easy to explain because it was why we started symbolic regression. And that's why we saw history, that how we did it. And you'll go to older work in like 2020. So tutorial by Malcolm, and we'll also talk about graph neural network, which Christian Jesperson will tell you about, and we'll actually use later on to paint galaxies better. Okay, so when we look up in the sky, can we predict what happened? We look at a bunch of planets moving around, time t equals t0 and t1, and they move around like that. Traditionally, what do? If we're Isaac Newton, have someone bring you food and have very relaxed life, and sitting under apple tree apparently, then you can figure it out somehow. It was very lucky, I think, also, and a lot of hard work. But I think I do not have the time and probably the genius of Isaac Newton. So we're going to use something called symbolic regression. What is symbolic regression? Is a bunch of mathematical functions we have now and variables. We'll form new equations, and for that algorithm basically checks whether the new equation fits the variable, the observables. Then we move on to the next new equation to find a better fit. So how do you choose what next equation to move to is, part of the secret sauce. But also possible issues you immediately see from here is that it's a very large space to search for the right equation. So how does neural network come in here? Because this one has no neural network. This is just a search. As you can see, there's no neural network here. Neural network comes in to crystallize the system down to as small number of variables as possible. That's what neural network had done. And I'll show you what we did. So for this planetary system is moving around, we use graph neural network, which we'll describe briefly, but Christian will tell you way more at the tutorial on Friday, so don't miss it, to make sense of the system and help to predict the dynamics first. So you want a neural network that actually understands the system first. However it understands it, we don't know yet, right? And then we hopefully find the equations later. But first, we make sure it predicts the dynamics. So we use graphical neural network to predict the dynamics. So what's graph neural network? Anyone knows about this already? Oh, we have a lot of experts, but there's some shaky hands, so that's good. I'll go into it. Question, you can't raise your hands. You should just Shirley, you should stop. I'll come. A graph is a natural way to represent entities and their relations. So we have nodes, we have edges. Sorry, I keep pointing into this. So nodes and edges, and we can infer about the entities and the relationship respecting the graphical structure. So the graphical structure does give you a prior on how things are related, right, at some level. So graphs can capture many complex object relation systems, the molecules, H2O, the rigid body system, balls bouncing four walls. And here the wall is represented by this light grayish bluish ball. And it only exert forces on the other one. So there is a prior you're implicitly applying when you set this up. And this is assuming that this wall is not going to move, right? It's a rigid wall. So we don't actually have forces applying on the wall itself. The mass spring system, for example, you have the spring, which is connected by many different nodes. So many nodes here. And the ball, which is this mass. And then you can see how, at the end of this, you're not going to point to nothing, or you're not actually circling to itself. N-ball system that you've seen a lot with the planetary system, right? So they are just fully connected graph here. They all connect to each other because they're all affecting each other. And you can also do sentence and parse trees with the brown dog jump. You can actually describe this as many nodes and edges. And you can also use graph neural network for image and fully connected scene graph. So if you talk to graph neural network, they will say graph is everything. There's a paper that recently said that everything's connected. Is that correct? Yeah. And that paper basically described graph neural can do everything, including transformers, I think, that we just talked about earlier. But personally, I think there are different things that more fitted for different scenario, such as, images. I would say you probably want to use a convolution neural net, I suspect, but you could use graph. So a lot of our work is based on something called interaction network from 2016 NeurIPS. Shocking. It's a really old paper in NeurIPS. There's a lot of a lot of things have happened since, but this is describing how you use the graph a little bit more in details. We have the nodes, we have the edges. We could have a global variable called U. You can imagine the total mass, total number of people in the party, total energy in the system. And then what we do is that first of all, we look at the edge function. What is the edge function right here? It computes the message from the node and edge attributes. So there's a bunch of attributes right here, right? That tells you which edges is receiving from which node, sending to which node as edge attributes, and there's a global variables. This will compute this message function from node and edge attributes, and then produce an update. And in this node function, which it receives all this information from all these different edges and aggregated all the messages and do an update on possibly the node. And so does this sound familiar to some people here? Yeah, okay. So what you do is that you try to model the planetary system we talked about with the graph neural network. I just show you how well we did. Here's the outcome again. The truth on top, the model in the bottom. Left-hand side is the planetary system. We looked at balls bouncing in four walls and mass spring system. And you can see that actually the n-body system is producing pretty well. And we're like, okay, that's not too bad. 1,000 step rollout means once you train the system, it basically produces a simulation 1,000 step by taking its output and feeding in for the next as input, right? So it's not too bad because any small mistakes is pretty dramatically exponentiated. Zero shot generalization means we're gonna ask the system do something it hasn't seen before. Not exactly, because it has seen other n-body system, but it hasn't seen this number of planets. So it cannot just memorize what it has seen before. It has to learn to go a little bit further, which assuming that the network has learned some physical, reasoning behind it, it can do a much harder system. So this is an n-body system it has not seen in terms of number of particles, number of planets. Same thing, it has not seen this number of balls. It has not seen such a long string before. It was still able to do it. So it says maybe it has learned something in that graph network, right? So if it's learned something, can we interpret it? So this is what we did. So how do you combine, you take the neural network and you say, okay, what are you gonna do? We're gonna force it to have as few parameters as possible. We've actually done many different directions of how to force it. This is one of the, things that we have done for this paper, but honestly, we've done many other things since then. So the first thing we try is that if the simulation is in 2D, then we do not expect the dimension of these edge factors to be larger than 2 or significantly larger than 2. If you limit it to 2 immediately, you make training much, much longer and the performance is not as good. Then we do something called the L1 regularization to minimize the number of message elements that are actually important to fit the observable. It really just means like take that number of messages and just say, okay, can I have like a small number when you add them together? And then we put these edge elements that we found here and try to fit for the symbolic regression package, right? So we have a symbolic regression package just does the search. We take only the elements that are important according to this neural network and fit it in and say, okay, what have you found? That's what we found. We actually fit and found the laws in springs for 2D and one of our R-square law in 3D. And so we're like, okay, this is weird. It actually works, this first thing. And then we try to do a little bit better, right? So this is what Miles gonna tell you about, which is Pizer. This is symbolic regression-based interpretation method for distilling and discovering symbolic models from deep learning, and in particular, graphical neural net. You will learn it today and this afternoon if you like. And we want to check if it works with some actual data. So we took the NASA Horizons ephemeris data that's orbits of all the moons and all the planets for 30 years and apply this, right? So not just joke around with simulated data, because simulated is beautiful, but not really real sometimes. Although I have to warn you that this data set is also beautiful because it's very accurate. The error bar is very small and you have orbit for 30 years, but only got 31 objects. So it's not too many objects. So we did use the orbits from our 30 years of observation, divide them into training, test sets, validation sets. And we found this law. Actually, it looks like something very familiar to a lot of people, one of our square law. And we also learned the masses of the moons and the planets. Here is the true masses versus predicted masses. Like we didn't tell it what the masses of the planets and the moons are, because otherwise it would be trivial. Here's the log scale in mass over in solar mass, all the different planets that you love and satellites and the moons. I didn't learn about all the moons until this project, to be honest, because I don't do any planets until recently. The truth is the star. This circle is the predicted. You see multiple circles here because what we did is that someone who do a neural network will tell you can initialize the weights of a network before you start training, right? And depending how you initialize it, you actually might end up with different minimum of your loss function, or basically what you want to search to find the correct predictions. And this is when you do different initialization for that particular moon, right? Different initialization of network, but a lot of them will actually land up exactly the same point. But things that we don't have very good control, you actually will have a very wide spread of what the prediction is. And this gives you a sense of the error of the network predictions, which is very useful. And we also found that the error that we predict for using this network would actually be inversely proportional to the gravitational influence of that object on the system. So the less influence you have on the system, the bigger your error is, and it's plotted right here. So we thought that was pretty cool, but we were sad we didn't find GR. So just to let you know, this is just, we found Newton's law, because GR's effect is so small. It's actually, it turned out smaller than the tidal effects from Jupiter for most of the moons and planets. So we can't find them, but we do find that there's a little bit higher error for example, some of the planets like Mercury. So, and if you look at the equations we find, the first equation is like Newton's law. The second equation is like an effective version of GR, but that's not preferred by the system because it depends on how you define the complexity of these mathematical functions. You basically have to go complex by like one more parameter, but then you don't actually decrease the loss or like the error by that much. So it decided to have a simpler equation and not go further down into complexity. Yes.
Wondering how many how many different random initializations do you average together to create the final model?
For this one, I don't remember, but probably like 5 to 10.
Okay.
Yeah.
Thank you.
Other questions? Yes, please, Eric.
I didn't understand the last bit about it finding an effective version of GR. Shouldn't that look like Newton's law? What did it find?
It's like plus an extra term. I forgot exactly what it looks like.
And it actually pulled that out.
It pulled that out, but it was the second preferred equation, not the first one. And you need to understand, we designed the symbolic regression package, right? Mm-hmm. And you actually give a complexity number for each of the expressions. Say somehow I decided that exponential is complexity 3 plus is. So these are somewhat arbitrary and subjective decisions. So I suspect what one should do, if you want to be very rigorous, is to try all types of complexity decisions and see what equations you find. But that would significantly change, I think, what equation you will find. As a scientist, I don't think you should depend on symbolic regression and say, this is the true God-given, equation. You should look at the 10 equations and like go work on it and see which one's correct. So I would say symbolic regression is a good tool for you to discover relations and possible physical laws that you would go in and say, okay, which one makes physical sense that follows all the symmetries that you believe is correct. So it's a tool. It's like a calculator, except it helps with deriving new equations instead of just calculating numbers. So that's what we suggest. So going back to painting galaxies, I know people are like huge detour with symbolic regression and graph neural network. We have talked about HOD that people all love and use, and there's SHAM, there's other versions of analytical formula. And then we have the riskier ones where we can have hydrodynamic simulations. We learn from it. You can do it map-based. You can do it like depending on the parameters directly. And we can even find equations. Remember the equation we showed you earlier that Anna Delgado's work has done? That was using symbolic regression on about 20 parameters, right? But it lets you search through all the possible combinations. that you can throw into that equation. So think of it as a great equation searcher if you have a small number of parameters. And a small number of parameters can be gained either by intuition that you have, like these are the halo parameters that you want to throw in, or you can use a neural network to compress your system into something that will have only a few, like 15, 10 parameters or 5. We can use many methods to learn from that one that we talked about. And if you don't think so, what do? Like we have other information, right? How about including other information beyond the halo, right? And that's what the maps were doing. And I think there are other methods we can do. So this is work by Christian Jasperson, who's sitting there. You can ask him if any complaints, go to me. If anything that's good, go to him. So we have the simulations here. That's the dark matter. And we also know we get merger trees from the dark matter simulations. And we know that merger trees will tell you something about the formation scenario of the galaxies. So the merger tree looks something similar to what we see before. Christian's like, yes. You know this one. Well, Christian doesn't want to say it's graph neural network. And he will tell you way more about this later. And how to work is actually fairly simple for neural network, actually. And he's going to model the merger trees with the graph neural network, including all the information that's not just the current time, but also previous time from the merger trees. Just to backtrack a tiny bit, we're not using Illustris here. We're actually using sham data from Rachel Somerville and her students. Austin, yes. Yeah. And then, so what we did is we identify halos in envoy simulations, we build the merger trees, and then you encode the merger tree as an abstract subgraph, and then basically predict the galaxy properties, not just the number density, but also multiple galaxy properties. I'm only going to show you one of them, but this is what the traditional method when you use abundance matching, you know this better than I do, for stellar masses. So this is the SAM, which is the ground truth here for us. This is the abundance method, right? So this is what we can get if you use abundance matching. But if you use graph neural network, that Christian will tell you more later, this is what you get for GNN, right? So graph neural network plus the merger tree, you can see a much more perfect correspondence. And you can see the Pearson coefficient is like 0.997, which is a bit insane. So, and there are many other properties of the galaxies that he has successfully predicted using graph neural network. So he sort of concludes a little bit about what we have talked about today, and I would like to take questions. So deep learning can do a lot, right? We went through like a whirlwind of many things it has done, even for just galaxy formation. We're able to accelerate some simulations. So Athena ++ simulations, no easy feat. And we also ping some galaxies quite nicely, right? Number density, we can ping stellar masses on the map form. We can do H1 hydrogen gas. We can even get, using the merger history to get a much better prediction of the galaxy properties, if you see. And we touch a variety of methods today on convolution neural nets, more symbolic regression, about finding the formula, like a search for the equation. Graph neural network, if you describe relationship data, like relational data, that actually helps you a lot to make your data easier to compress at some level, because if it's a map, it's actually really hard to compress. We also touch on transformers and diffusion models, but more as like, on the side. We did have a paper that used the transformer models that does generate these like videos and images for predicting turbulence simulations. And I'm happy to talk about it as well. And I think that's it. And the diffusion models too. So this is some real conclusion, not really sure I have one, but the same ideas like diffusion models here that's used to generate this couch potato picture also generate the simulated universe on the right-hand side. This is work by a visiting student from Mila in Montreal. And I'll stop here and take questions. Thank you. Yes.
Really cool. For someone that doesn't really understand anything about symbolic regression, when you try and run this to get the relationships of the different formulas, do you ever get results that, like, at first glance, don't seem physical between the parameters in the formulas? And do they describe well the thing you're modeling? And how do you compare that to things that look more sensible?
Yeah, so we actually did way more about symbolic regression since then. So I talked briefly about how we want to simulate the turbulence simulations, find the correct equations, and find the closure terms. For those who don't do this, I don't also do this until recently, is that there are sets of equations that describe the turbulence simulations. And you can put in these simulations put in this equation in simulation, it runs forward. But if you put in a low resolution versus a higher resolution simulation, you all know they give you different things, right? So what's different between the high resolution and the low resolution simulation can be described sometimes by these closure terms. And this closure term is not something that we know a priori. There might be one or two examples that have been found by very smart people that these closure relations were named after them. They were so smart. That would help, for example, to accelerate turbulence simulations on modeling our ocean, right? So people have been trying to model our Earth because we want to know long-term projections of ocean's temperature. That's actually, I wanted to show one of these simulation movies for that one. And if you can find these closure terms, you can run low resolution simulations with high resolution components in them. And that's actually sort of a holy grail in not just oceanography, but I can also imagine any turbulence field. So that's what we're trying to do. And we have found many equations looking at multiple different types of turbulence simulations. And some of the equations we found are not necessarily physical. For example, so the X, Y, Z direction, you should expect to have the similar formula. But sometimes they don't. And then you look back and say, oh, because the flow is in one direction. It actually changes what the equations will learn because all the examples we gave it was going like flow, laminar flow going in one direction, for example, right? So there's nearly always a reason why you find something you don't expect. You also have to just work really hard because you don't have perfect predictions, right? This is the loss function I'm just drawing. It goes slower, but sometimes you have another bump that can go lower and you don't know whether you have plateaued. So there's a lot of back and forth between making better predictions, going to a smaller loss function, and then trying to fit for the equations. But I'm really excited about the closure relation problem, actually. Other questions? There are no questions. I can show all the things. Yes. Okay, the chair decides. Who's the chair of the section, I guess? Mhm.
Jessica, did you? Okay, yeah. Whoever's online, feel free to unmute.
I think there's also one person raised their hands in the back as well.
Yeah, so a person online was me, unless there might be someone else, I don't know. Great talk, Shirley, thanks very much. I learned so much. I think I'm going to have to view this another couple of times. I have one question for you, and it goes back to the discussion we just had after the short talks, is what is your hope in terms of accelerating hydrodynamical simulations so that we can start maybe increasing resolution, putting in more ingredients, and maybe learn something more than we already had before. Maybe I'm over optimistic, but so
I'm a permanent optimist, to be honest. I think it's a training from being raised in California. It's the sunshine. So I think there's a lot to learn. You make these simulations, you can make them high resolution, different parameters, right, that you can put in. But as someone who works very closely with data, I think you cannot get away with comparing with data and how would you link back to a comparison with data, because otherwise you'll always just imagine new things to do, which are physically interesting to try. And I think talking with theorists to say what is physically reasonable and, natural, I guess, in some ways would be very useful. I really like to see people trying to push more to analyzing the data. There's a lot of data right now out there. We spend billions of dollars. We'll spend billions of dollars in Euclid and Roman, and we have CMB data that looks at SC clusters, and we're not super utilizing them yet. I think we will hopefully do more, and I think CCA, with Rachel, very interested in pushing in that direction and getting observables out from these simulations will be very excellent. Pacos has done a lot of work in terms of pushing simulated-based inference too, and we have for different reasons. I push for cosmological parameters. I think he's very interested in the astrophysical parameters as well, and Mark as well. So I think there's a lot of work in that direction. I think we all have to do everything together. Get more money, yes. to analyze the data, but also talk to theorists to make sure that what you create is not just like a weird model. We have something similar in cosmology where we can create a really weird dark energy model that will fit all the data at some point, but it's like just a fit. It doesn't tell you physically what happened. So we need to go beyond that. And I think taking that step beyond that will be very exciting, and interesting. A question in the back?
I'm not sure if my question is very initiated, but as an observer, are there specific parameters about turbulence that you would read the paper where I measure the line widths in H1CO and ionized gas in various physical environments, and that would help you? Or is it more of a kind of algorithmic advance that will push this problem forward?
I think we need both, to be honest. I don't know much about line widths. I know a little bit, but for example, we have a lot of CMB data right now that has measured these SC clusters, right? And the predictions on SC on these big clusters in simulations are quite far from what has been measured. And these are, CMB data is quite clean coming from astronomy data, to be honest. So, and they have stacked thousands of clusters to find these signals. And if we can't even say, oh, then what are we going to change from the simulations and the theory side to get to close, the loop with even cluster, which is bigger stuff. I mean, the smaller stuff is even harder, I think. But maybe people think smaller stuff is easier because it's more linear. So, I mean, this is a lot of questions about, how about laminar force, which is way, more closer to linear. That might be closer to what simulations can get at more correctly. Big clusters are more complex. There's more, stuff's happening, things are exploding, right? So yeah, I think bigger stuff easier to observe. Nearly linear stuff is harder to observe, but nearly linear stuff is easier to model. So there's this crosstalk here.
Okay. Well, let's give a hand for Shirley again.